Swayam Prabha. Digital India. Educated India.
In the previous lectures, we saw how we apply the concept of angular momentum to solve rigid body problems, and we mainly focused on conservation of angular momentum for bodies moving about a fixed axis. In this lecture, we are going to start with the motion when an external torque on a body is applied. For example, let me show you. I will take this scale and hold it on a horizontal position like this and leave it. Take on the horizontal position and leave it. What I would like to know is, when it reaches here, ignoring friction, what is its angular speed? So, the problem that I am solving is, I have a scale like this. It can rotate about this point O, for example, and when we leave it, it drops down like this. And I would like to know what is its angular speed, omega, when it comes here. I will solve this problem in two ways, show you what a wrong way. So, let the length of the scale be L, so that its center of mass is at L by 2 if it is a uniform scale. Let its mass be m. So, first let me apply energy conservation right away. When the scale falls, its center of mass drops down by a height of L by 2. So, the energy gained should be equal to m g L divided by 2, and all of this energy gets transformed into its kinetic energy, which in this case is the rotational kinetic energy, about point O. This is point O, I remind you, and this is going to be equal to 1/2 I about point O, which we have seen in the previous lecture is ml square over 3 times omega square. The two should be equal, and therefore, I have 1/2 m L square over 3 omega square is equal to m g L divided by 2. This m cancels, this 2 cancels, one of the L's cancels, and therefore, I get omega equals 3g over L square root. So, this is the answer that comes from energy conservation. Second way is by applying the equation that dl dt is equal to external torque, and let us apply that. Let the position of the rod be at an angle phi from the horizontal. At that point, all the force acts here mg, and therefore, the torque that is being applied is going to be equal to mg L divided by 2 cosine of phi, because this distance is L over 2 cosine of phi, and this should be equal to dl dt, which is nothing but I about point O d omega dt, and therefore, I should have I, which is the moment of inertia, d omega over dt is equal to mgl divided by 2 cosine of phi. As I already have mentioned, I is m L square over 3, omega is d phi over dt, and therefore, d omega over dt is d2 phi over dt square, and therefore, the equation when the rod is at an angle phi from the horizontal is going to be m L square over 3 d2 phi over dt square, which is I alpha or I times the angular acceleration, is equal to m g L over 2 cosine of phi. L cancels, m cancels, and therefore, I get L over 3 d2 phi over dt square is equal to g over 2 cosine of phi. Since the left hand side involves t, we will use an old trick that we have used earlier in deriving energy conservation, and that is to write d2 phi over dt square as d over dt of d phi over dt, which is nothing but d over d phi of d phi over dt times d phi over dt, which can be written as 1/2 of d over d phi of phi dot, which is d phi over dt square, and therefore, the earlier equation becomes 1/2 d over d phi dot square, which is nothing but d2 phi over dt square, is equal to m g L over 2 cosine phi, and there was an I here, which is m L square over 3. I had simplified it earlier, I will do it again. The m cancels, this 2 cancels, one of the L's cancels, and therefore, I get d over d phi of phi dot square is equal to 3 g cosine of phi, and therefore, integrating, which is d phi dot square equals 3 g cosine of phi. There is an L also here, which I can write L here. This is for a rod which is of length L, and this angle is phi, and this gives you L phi dot square is equal to 3 g sine of phi starting from 0 to angle pi by 2 when it comes to the vertical, and this gives you phi dot square equals 3 g over L, which is the same answer as obtained earlier. So, I have used energy conservation directly, and I have also integrated the equation of motion, which essentially by this transformation comes to energy conservation along, energy conservation by itself. Now, you may ask at this point, why did not I do one more thing? Why could not I do that 1/2 m v center of mass square is equal to m g L by 2 when the rod came from here to here? After all, it is the center of mass which is moving, and it moves with a speed v c m, and this should be equal to the gain energy because of the potential energy drop. What is wrong with this? What is wrong here is that you have to be careful when there are extended bodies involved, when velocities are distributed over the body, when forces are distributed over the body, that what all is happening. For example, here if I start with this position, here is the center of mass. When the rod comes in this position, not only has the center of mass moved, you see with respect to the center of mass, the body has also rotated like this. So, in coming down like this, the scale is performing two motions. The center of mass is moving, and the scale, as you can see, is changing its orientation with respect to an axis passing through the center of mass. It is rotating, and it is rotating exactly by the same angle as it was rotating about O. So, actually the motion is 1/2 VCM square plus rotation about Cm, and if you calculate the kinetic energy, it is always Ke of Cm plus Ke about Cm. It will come out to be 1/2 mVcm square plus 1/2 I about Cm, which will be ml square over 3 omega square. Omega by definition here is going to be Vcm divided by L by 2, which is 2 Vcm divided by L, oh sorry, about center of mass, this should be 12, not 3. It is 3 about the point O, about Cm it is 12. If you substitute these numbers in, you get precisely the answer that you got earlier. What you may ask at this point is, but what about the torque? Torque, the forces are also distributed, but I took torque to be acting at the Cm. Because the torque depends linearly on the distance from the pivot point, its average comes out to be as if it is acting on the center of mass, but not when I calculate the moment of the velocity, because that becomes r times r omega. It depends on it as r square. So you have to be careful when we are talking about rigid bodies and distribution of forces and velocities over the body, that we take proper consideration of rotation and angular momentum also. As an extended example of this, let me now take this booklet. I will keep its printed side on top and drop it. I will keep the printed side on top and drop it. You see, the printed side has gone down. Let me do it again. I am keeping the printed side up, dropping it roughly from 1 meter, and let us see what happens. The printed side goes down. Can I explain this? In fact, there is a very famous book based on such a thing. The book is known as Why the Toast Lands Jelly Side Down. It has been generally observed, if you are applying jam or butter or jelly on your toast, if it drops from your hand, roughly the jelly side always goes down. Let us try to understand this using our rotational dynamics. So roughly I will take this book, which is, let us say, of the order of magnitude about 20 or 15 centimeters wide, and I was holding it here. What it did was, first it went down like this, it rotated about this point until it reached an angle when it slipped off. Once it slips off, it starts falling down, and when falling down, it rotates. What we observed, it rotates roughly by 180 degrees. Why roughly? Even if it is 150, it will fall down the other side down. Even if it is 200, it will fall down the other side down. So let us try to understand this. First step is, when the booklet is like this, let the length, the distance of the center of mass from the pivot point, or where I am holding it, be L. Then it experiences a force mg at the center of mass and a torque mgl, and therefore it should have an angular acceleration which will be I times alpha. Alpha would be equal to mgl divided by I, which is ml square over 3. 1l drops out, m drops out. So the angular acceleration is roughly 3g over L. It covers an angle theta which will be equal to 1/2 alpha tau square, where let me write tau as the time when it slips from the hand. So, theta is roughly alpha tau square. What should be the value of theta? We know from mechanics that if a body is at an angle such that this is theta, this is mg, theta 90, this is 90 minus theta, this force would be mg sin theta, this force component would be mg cosine theta. So, if mg sin theta roughly becomes mu times mg cosine theta, then the body is going to slip off my hand, and therefore, I can write tangent theta roughly equal to theta for theta small equals mu. So, when mu equals 1/2 alpha tau square, this booklet is going to slip off. Let us take a typical value, mu equals roughly 0.2, alpha is given to be 3g over L, which I will take to be roughly equal to 3 times 10 over 0.1 meters. So, that comes out to be roughly 300, and therefore, I have mu which is equal to 1/2 alpha t square, 0.2 equals 300 divided by 2 tau square, or tau, the time for it to slip off is going to be 0.4 over 300, roughly 1 over 750 tau square, and therefore, tau equals 1 over 750, which I can write as maximum 1 over 30 seconds. So, we have come up to the point where the toast or this booklet came here and slipped off. This time tau is roughly 1 over 30 seconds. In this time, it has gained an omega, which is alpha tau, and after it slips off, that omega remains a constant and makes it rotate. So, this is roughly equal to 1 over 30 times 300, which is equal to 10 radians per second. If this dropped by 1 meter, then the time taken for it to drop would be given by 1/2 gt square equals 1, t equals 2 over 10 square root, which is roughly 1 over 2.5 seconds. And therefore, you see that the angle by the time it comes down would be equal to omega times t, which is 10 times 1 over 2.5, which is 4 radians. That is slightly greater than 180. So, that is roughly the angle through which the book rotates, and you see it drops the other way. This is an interesting problem where we applied the ideas learnt so far.